Good evening for everyone. Now we can start evening session. Complex media, micropolar theory, chemomechanics, acoustic, metamaterials, and each other. I'm Olga Loboda, chairperson, and we have 5 minutes for each presentation. And after that, we have discussion. If you have questions, you should up your hand. And now I would like to invite a first speaker, Sabina Isaeva from Peter the Great, St. Petersburg Polytechnic University. Please, Sabina.
Good evening. Today I would like to talk about the influence of the external followable body torque on plane waves in the isotropic elastic linear reduced Cosserat medium. First of all, reduced Cosserat medium, it is a continuum with rotational degrees of freedom that does not react on the micro-rotation gradient. What we know about linear elastic isotropic reduced Cosserat medium? First of all, that they have a band gap. That is a single negative acoustic metamaterial. We know that viscosity in constitutive relations change the wave propagation in our medium. So, what we would like to know? We would like to know how the external followable torque influence on the wave behavior. For this case, we consider the loss of dynamics. We consider the stress tensor, and we can get our equation of motion in displacements. So we will get the spectral task, and after that we will get dispersional relations. Based on received dispersion relations for the shear rotational wave, we created a dispersional curve for an elastic isotropic Cosserat medium under an external elastic moment. We can see that that will be a band gap, so it's obvious, but comparing these results with a depression curve for a reduced isotropic Cosserat medium without the influence of the external torque, we see that the elastic following moment in our case reduces the band gap and increases the value of the boundary frequency and the cutoff frequency. So what it means? It means that the positive following elastic moment reduces the band gap, but it doesn't destroy it. However, using a negative tracking moment that does not lead to the instability, we will get the opposite effect. What will be if we had the viscous following torque? Well, answering this question, we will get the dispersional relation for the shear wave, but in complex variables. To avoid this factor, we dimensionless our wave number and got the real part of the wave number and the imaginary part of the wave number. Analyzing the equation for the real part of the wave number, we see that the band gap will disappear. We observe the section of the falling dispersion curve and the disappearance of the band gap. This tells us that the viscous following moment transforms a standing wave into a traveling but decaying wave. The presence of the falling section suggests that due to the viscous tracking moment, we can change the type of our acoustic metamaterial. Note that for a large dissipant parameter, the section of the falling dispersion will disappear. What we can tell about the imaginary part of our wave number. Well, our wave rate will depend on imaginary part. A numerical experiment shows that in the former band gap, a following viscous moment contributes to a slower wave attenuation. So, in conclusion, I would like to tell that comparing our results with the case of the zero external influence, it can be noted that a positive elastic striking moment increases the speed of the shear waves at a low frequency and pushes the band gap to the region of the higher frequencies, reduced to its wave. A viscous striking moment completely destroys the band gap, while with a note very high viscosity, a falling section of the disappearing curve will appear. A negative viscous moment, as expected, leads to instability. And a viscous follow-up moment reduces the attenuation of the wave in the following band gap. Now, that's all what I wanted to tell you in my case. Thank you for your attention.
Thank you very much, Sabina. And next presentation will be given Piatysheva Alexandra, Peter the Great, St. Petersburg Polytechnical University.
So let me introduce my presentation connected with the influence of inner dissipation to behavior of reduced Cosserat medium. And as Sabina already mentioned, reduced Cosserat medium is a continuum whose point bodies have rotational degrees of freedom. And we will work with the case of reduced medium where we have no gradient of microrotations. So, and firstly, I would like to show the behavior of this medium without any dissipation, and we can see this colored wave number and infinite large imaginary part. And the aim of work was to see how the behavior of dissipation curves will change with addition of viscosity. So to investigate this question, we had to use some equations from mechanics, and here you can see them. So, and we worked this dispersion relation for shear wave. Yes, we investigated only shear waves. And firstly, we added translational viscosity, and on the right side you can see how it changed behavior of real part of weight number, and so solid line shows us the behavior with dissipation, and we can see that no longer we have zero real part, and no longer we have a very big imaginary part. So due to it, we can understand that now our wave are traveling through the medium, and it's a very interesting moment. So also we did some approximations to estimate behavior of dispersion curves. So, and here you can see comparison for small situation, comparison of numerical and analytical solutions. So they fit each other quite nice. And also we saw behavior of logarithmic decrement, and so the conclusion was that due to dissipation, dissipation helps to wave propagate into previous band gap, and also it increases absorption of wave outside the previous former band gap. So, and then we added rotational viscosity, and so we had kind of the same result. And, So you can see again here numerical solutions. Dotted line is again for elastic system, and solid lines are for system with dissipation, and we have the same behavior. And again, some approximations. And yes, here we had a little bit more of approximations. That's because we didn't approach too close to critical points, and the behavior of logarithmic decrement changed, and no longer is an infinite one, but it has maximum inside the formal band gap. So, and again, dissipation helps to the wave to propagate inside the colored zone. So, and here's you can see conclusions, but I told along the presentation. So thank you for attention, and I think I've finished. So
Thank you very much, Alexandra. And I would like to invite next speaker, Sargsyan A from Armenia State University of Shirak.
Yes, hello. I need to told that as structural elements, thin rods, plates, and shells are widely used, the bearing capacity of which is determined mainly by their stability. Theory of stability of thin rods, plates, and shells in the framework of the classical theory of elasticity is described in the monographs of Timoshenko and Volmir and others. The work of the Shorkin is devoted to the stability problems in the framework of the micropolar theory of elasticity and review of the works of the micropolar theory of thin plates and shells was carried out in the work of Yeremiev, Altenbach. In our works with Professor Sargsyan, the linear and nonlinear theories of the micropolar elastic thin plates and shells are constructed, and also many dynamic and static problems are solved, and stability problem of micropolar elastic rectangular plates and shallow shells are solved. In this work, problem of the stability of the micropolar thin round plate is considered. So we consider plate of the constant thickness of 2h and as a three-dimensional elastic isotropic body, we assign the plate to the curvilinear coordinate system alpha 1, alpha 2, and z. The coordinate plane alpha 1, alpha 2 will be combined with the median plane of the plate. The axis OZ is directed along the normal to the median plane. Here need to use the basic equations and the natural boundary conditions of micropolar elastic geometrically nonlinear thin plates with independent fields of displacements and rotations in curvilinear coordinates, which I obtained in my earlier work. So we have the balance equations 1, elasticity relations 2, and geometrically relations 3. Also, we need to join the boundary conditions 4. In these equations, there are involved displacements, complete rotation angles, also the free rotations in the initially normal elements around the axis, intensity of the free rotation around the axis z, elongation and shear deformations, flexures and torsions of the plate median plane caused by the stresses, and also flexures and torsions caused by the coupled stresses, hypershears, of the plate, median plane caused by the hypothesis. Also here involved the averaged moments and forces from the stresses, and averaged moments and hypermoments from the hypothesis. In the case of a round plate, from the above equations, we can obtain the basic equations, balance equations, 5 physical geometrically relations in the form of 6. And also we can obtain the, these equations in the case of axisymmetric problem. It will be in the form of the 7 and 8. Then let us consider micropolar elastic round solid plate under the action of radial compression P, which is uniformly distributed along the contour. The flat strain state has been implemented. We will call it the main subcritical state, and it is the solution to the linear system of equations of the generalized plane stress state of micropolar elastic thin round plate. It is the equation, balance equations 9 and the physical geometrical relations 10. Also, we have the boundary conditions 11. For this problem, we need to note that the components of displacements, deformations, force and moment stresses corresponding to this stress strain state are marked with superscript 0. In case of loss of stability, subcritical stress strain state will receive some disturbance. The values characterizing the stress strain state will receive some disturbance, and the values characterizing this strain state caused by this disturbance will, we imagine that they are marked with the asterisk at the top. The perturbed stress strain state in the plate is characterized by the values of the corresponding sums with indexes of 0 and asterisks. Perturbation are small, and during the transformations we will neglect their powers higher than the first. It is easy to notice that the solution of the subcritical boundary value problem, above boundary value problem, have the form 12, and we investigate the stability of round solid plate of radius R with the hinge supported contour and under the action of radial compressive forces P uniformly distributed along the contour of the plate. We substitute the noted total relations into the system of equations of the geometrical nonlinear theory of micropolar plates. It is the system of 7 and 8. Then we obtain the equations of the perturbed stress state in the form 13-14. Balance equations and physical geometrical relations in the form 15 and 16, and corresponding boundary conditions 17 and 18. So it divided to the two problems. Problem 13, 15, 17 has trivial solution, and problem 14, 16 and corresponding boundary conditions 18 can be reduced to the following form with respect to the displacements W and rotations C1 and omega 2. 19.
I'm sorry, but your time is over.
Just 1 minute, please. In the result of this solving to this differential equation, we have the solution in the form 32, 33, and 34. Here we use the Bessel functions of the valid argument of the zero and first orders, and for the obtain critical force P, we have the equation in the compact form of 37. Here we also use the Bessel functions, but only a polarly imaginary argument of the zero and the first orders. We consider specific numerical example for hypothetic material. In this figure, it is demonstrated the dependence of the dimensionless quantity of the critical force on the dimensionless physical parameter alpha. And it is easy to verify that with increasing of the dimensionless parameter alpha, the value of the critical force increases, which means that in the case of micropolar materials, the round plate is more stable. Thank you for your attention.
Thank you very much. And next presentation will be given by Malinovskaya Elena from Obukhov Institute of Atmosphere Physics, Russian Academy of Science.
Hello, everyone. Let me show you my presentation, a numerical study of the effects of surface microstructure of the airflow. Here we try to understand how changes in microstructure of soil surface influence the emission of dust particles. Three tasks are considered. The first is moving of airflow near surface particles with the structure homogeneities. The second is the study of effects of surface structure in homogeneities with the local changes of distances, orientation, and inclination. The third is the moving of the airflow near aeolian structures. The emission of dust particles is associated with the presence of flux of saltating particles. This term saltation means bonds with the sediments. This flux becomes stronger with an increase in the effective roughness high and has a cubic dependence of the friction velocity. So it is mean that very important to study influence of surface on airflow and dust particle emission. The sand particles have a middle size about 200 micrometers, and here you can see some information about sizes of our land structures and wind velocities over various elements of some aeolian structures. The most probable distance between particles estimated with the using of sand porosity and of result of randomly numerical generation particles whose sizes correspond to the normal distribution. The changes of distances between particles for different orientation and inclination also estimated. Numerical experiment had made with the open form, with the central form solver and utility SnappyHex mesh with the 4 levels and minimal scales 1 micrometers. Buoyancy force acting on particles in a layer is higher for case when distance between particles equals its size, and grows for distance less than 50 micrometers. It is very important result because it is mean that we should study processes with including effect of porous medium. Effect of surface structure and homogeneities studied with the turbulence model with using open form for local changes, distances, orientation, and inclinations of surface. The influence of local changes of distances become to increase in the pressure differences at opposite edges of the particles and an increase in the buoyancy force. The same effect found for cases with a change in orientation and inclination. All these factors indicated that the sand surface under the constant influence of the wind is an alternation of quasi-regular regions in which the surplus of the pressure difference above and below below the particles prevail over gravity. With using simple model of changing lines of the windward slope and satellite data found that on top of the dune particles is more stable for wind blowing. It can be explained one of two possibilities. First is an increase in threshold friction velocity when moving up the windward slope, and another, the increase in roughness and resistance closer to the top. The flow about micro ripples with a height about 1 millimeters was considered at air speeds of up to about 4 meters per second, at high about 2 centimeters, using the less model of open foam. It is shown that the addition of elements of heterogeneity at the apex of the rough structure is the streamlined aeolian structure leads to a shift of the separation point of the ascending floor to a change in the length of the recirculation zone. So here is my conclusions and some reference about this term, and also my contacts. If you're interested in this term, you can write me. Thank you.
Elena, thank you very much. Next, I would like to invite Riabokon Evgeny from Russian Federation, Perm National Research Polytechnic University. Please.
Good afternoon, ladies and gentlemen. I will briefly introduce you our small research on static and dynamic loading of rocks. So, at the beginning, we will quickly go through the following sections, such as determination of quasi-static mechanical properties, and then we determine those properties in dynamic loading. I will say a few words in section 3 about the experimental rig we designed and obtained results, and we will finish by conclusion. Well, actually, our small research represents a full cycle of rock study, from its manufacturing till its properties determination. So there were, at point 1, there were 4 types of specimen produced. The difference between those specimens was in diameters and length. Each of specimens went through coring, grinding, washing, and drying. So they belong to Permian age sandstone, which is widely spread over the world. So we wanted to determine its mechanical properties in static and dynamic regime, and then compare them. And also we want to apply Brazilian method for tensile strength determination. For each diameter of samples, we did 9 experiments. So 9 experiments. So firstly, we studied samples on standard rigs such as Tinius Hounsfield and Instron. While increasing the diameter, there was an increase in uniaxial compressive strength. So you might see it here that while increasing the diameter from 7.1, 9.2, 11.5, 24.7, the compressive strength will increase 38, 43, 53. Basically, we found classic stress strain curve and fracture mechanism. Then we determined tensile strength by Brazilian test and noticed that the average value of tensile strength, which is presented here for each diameter, was less than compressive strength, which is here, in 10 to 20 times. And also we've noticed standard behavioral fracture. All the experiments were performed according to standards such as ASTM and ICRM. In order to see how different the mechanical properties will be in dynamic loading, we designed a small experimental rig, which is presented on this slide. Here in the middle, you might see the sample loaded by constant static weight, static load here, and by dynamic force produced using magnetostrictive actuator powered by a signal generated, at which we could change frequency and amplitude. So during experiment, it was shrinking and extending, applying dynamic load just on top of a sample. Two sensors recorded samples deformation, such as laser sensor and eddy current probe. So laser for longitudinal, for horizontal displacement, and eddy current probe for vertical strain. The sensors were calibrated here, and on the bottom you can see a perfect match of one sensor calibrated to more with more resolution. Then, in order to be an inelastic zone and due to restriction of load applied to an actuator, which was 1 kilonewton, we had to use the smallest possible sample in diameter. So 7.5 millimeter samples were produced at the beginning. I mentioned one of the sizes. So we had to be in these conditions. So on this slide, you can see how that sample was deforming during experiment. And one is a laser sensor, and number two is eddy current probe. So they were measuring accordingly longitudinal strain and transverse strain. You might notice that longitude, and on top you can see dynamic load as well. You may notice that the peaks of dynamic load corresponds to peaks of longitudinal deformation. And it also corresponds to the smallest peak in transfer determination, which is quite logical if we go back to this behavior, and we will understand that as soon as it shrinks, the space between eddy current and this metal disc will increase. At the same time, space between laser sensor and sample will decrease. So we created several regimes, actually 30 regimes, depending on frequency, different frequency and amplitude. And with help of force sensor, we were able to recalculate all these recordings and obtain one of mechanical properties, such as Young modulus. You may notice that it's increasing slightly over the increase of frequency and amplitude of dynamic force, which is not quite typical if you look in papers, in scientific papers. So we believe that this behavior is caused by energy dissipation, and we will work on that while while optimizing our installation a bit later. So then, as we determine as we settled all the installation, we determined dynamic mechanical properties, and particularly we applied Brazilian methodology for testing and determining tensile strength in dynamics. And here you may see the results which we obtained. So Brazilian tensile strength versus uniaxial compressive strength. So at the end, the conclusions which we made. So Young modulus of the sandstone increases with increased value of dynamic load and frequency. Under vibration, dynamic mechanical properties of sandstone are less than those determined in static experiments. Uniaxial compressive strength and Brazilian tensile stress of the sandstone specimen decrease with increase in its diameter, and Brazilian test can be performed in dynamics using an experimental rig with a magnetostrictive actuator. So those are papers which have big influence on our research. And if you have
Thank you very much, Evgeny. Time is over. And next presentation, I would like to invite Shorkin Vladimir from Oryol State University.
Good evening, dear colleague. Our report theme is assessment of damage caused by occurrence on uneven mechanical properties. Machine parts have new properties only in their limited part. The distribution of properties over the materials of the part is uneven. It can be uniform on different parts with jumps on the surface of their contact, or uneven without jumps on their properties. With this change in the properties, damage may exist or may absent. Our model, solid body, we divide it on parts, and parts interact between each other with potential forces. Potential forces between parts, delta B part of the well body, A R alpha is surface of our body. So our model. Non-local interaction of solid particles and their potential energy is in these formulas. And non-local model and local model consists of non-local model. Phi is potential between particles. We considered two types of damage. First type is continuity of material is preserved, but the coherence of atomic lattice is violated. In the second case, both the continuity of the material and the coherence of its atomic lattice are violated. If there is no defect in the body, then surface A is absent. If there are defects, then surface A1, 2 is present. Such without defects, here with defects. It is assumed that there is damage. Defects are distributed discretely. Each of them has its own particles. You can make a section of the particles that intersect in depth. The criterion for assessing damage is relative real beta of the defects in the cross section. It is assumed that the size of particles and therefore the cross sections tend to zero. Any infinitesimal particles contains a flat defect on an infinitesimal area. An arbitrary cross section of the body is made. It is assumed that any part of its passes through the defect is divided a particle them into the particles them, the iodine, and the above. At the outer boundaries of the particles, the iodine and the them disturbance from defects tend to zero. Therefore, the problem of adhesion of two semi-infinitive bodies along the surface R12 is considered. Particles DD1 and DD2 are considered continuous. Displacement their gradients with stress tensors and are defined by the following equation. Result of solving the problem: expression on elastic strain energy as a functional of a function beta. Beta-like function of F. Potential function.
Yeah.
Potential energy, like function of R and beta at F. The function beta delivers a minimum of this functionality. There may be cases for different parts of the surface R at in 1. If beta more than 1, this means that the entire part is damaged. If beta less than 0, the entire part is not damaged. When beta between 0 and 1, part is partially damaged. Using a set of surfaces, you can identify the distribution of damage. For even distribution of damage, beta, like 5 function of R, and like constant. W is a square form. The damage parameter is determined from the necessary condition of local extreme by using the formula for beta. Here we work of a generalized force that corresponds to the first index is on generalized displacement that corresponds to the second index. An example is considered. The result volatility corresponds to the definition of effects of red crystal of oscillator. Thank you for your attention.
Thank you. And please, next speaker is Grigorieva Polina, Peter the Great, St. Petersburg Polytechnic University.
Hello. So I will be brief and tell you about the mutual influence of hydrogen diffusion on the linear elastic properties of the steel. From where we start, from the actual problem happening everywhere, it's well known one, hydrogen embrittlement. It's the process when metals become brittle and have a lot of fractures because of the infiltration and diffusion of hydrogen into the metal from the external environment. And this can happen at a micro level. Crack going grains, and on micro level, a huge crack after the fatigue or something like this on the micro level samples of metal. What is new and why actually I'm interested in this? Last experiments show that the first hydrogen diffuses not only from aggressive corrosive environment, but also from the air. Metal can catch hydrogen from the water vapor, which is in the air. So basically, hydrogen embrittlement happens not only in some corrosive environment. Second experimental fact is that low concentrations of hydrogen also affect mechanical properties, and they do it much. So a lot of models which propose that hydrogen affects those metals only at high concentrations, they don't work actually. And also the last results are the results of hydrogen distribution. So a lot of results as some mechanical experiments show that first hydrogen distributes highly heterogeneously, and it forms a boundary layer. And also this boundary layer affects metal and its properties a lot, because there exist some experiments showing that when we remove this boundary layer of about 100 micrometers, metal is again not brittle at all, and doesn't have fracture as it has. So actually, again, we have to have a model which explains this boundary layer, how it appears and how it affects the mechanical properties. And I'm working in a huge team working on this problem. And my challenge actually to explain the forming of this boundary layer using some diffusion models. So start again with the experiments. How hydrogen fuses into the metal. There are a lot of models saying that ions of hydrogen diffuse not hydrogen, but experimental results show that electric charge on the surface of the metal samples is not observed. So actually it's not an ion of hydrogen. Also, there are some models saying that molecules of hydrogen break into atoms near the surface, and then atomic hydrogen diffuses. But also the heat which this atom produces is not observed. I'm saying about hydrogen embrittlement in, of course, in usual environment or in acid or not very corrosive environment, not saying about some hydrogen embrittlement in the nuclear stuff in this. And so the main point is that the molecules of hydrogen, they're quite small, so they can diffuse through the lattice of the metal. And we assume, again, basing on experimental results, that hydrogen diffuses in two ways, through lattice and by trapping. And also there are a lot of models using trapping, traps and trapping diffusion. The problem is that they're purely empirical and depend on a lot of constants, so that cannot be used in a wide range of experiments. And the second point is that they ignore that traps catch hydrogen because of its high activation energy, so they neglect some chemistry and thermodynamic stuff lying before after this diffusion. So what we use non-equilibrium thermodynamic approach. Sorry?
Вот это там есть.
We use actually the approach of Prigozhin and Ansager, saying that diffusion flow depends on thermodynamic forces and Ansager coefficients. Thermodynamic force is actually a gradient of control, and as we are looking at gas diffusion and neglect everything what happens with metal, we just need to take into account how metal and its potential affects diffusion of the gas. So we just use well-known chemical potential of the gas and chemical potential of the solid, which is actually energy momentum or HLB tensor, which is quite known. Then we obtain a new equation of diffusion. Not overload with the matrices and equations, just go to the diffusion equation. Just want to notice that when we write stress strain state, here we just neglect all the plastic stresses and strains appearing in the metal. Just because for the first we want to verify our model and see if it would work and describe this boundary layer formation. So we use a linear elastic model of the metal. And we also say that there is an induced strain which appears because of the diffusion of the hydrogen in the metal. So there is some induced diffusion strain. So basically we obtain a new diffusion equation where the viscosity coefficient and the structure V depends on concentration and strains and also gradients of strains. And to solve any problem, we have to solve a coupled problem because we have to solve a plasticity problem. Now we have to take into account this induced diffusion strain. And what actually we've done, we solved the problem for a cylindrical sample, which has applied stresses on subordinate. What is actually happening in all the fatigue tests of this kind of values and samples where hydrogen diffused from the outer boundary. And here you can see the dependence at times dependence of the concentration on radius. So first we can see that well, of course it doesn't form a boundary layer, but still the diffusion goes down, and it's not linear or quadratic, etc. How it's in usual fixed flow diffusion. And the second we see that is change these three pairs distribution depending on time, and we see that with a growing time, the diffusion stops and concentration profile changed very slightly. That means something appears in the diffusion, so that it also gives us the hint that probably the gas will stop and form a boundary layer. So actually that's it. We follow the steps of the Gaussian model to write the diffusion equation of hydrogen, and of course we obtained something more or less corresponding with our experimental results, and we checked the advantage of the possibility of this model, because now we can add some rating based on chemical activity and so on. We can add plasticity, some changes in constant parameters of the material, and the great advantage of this model is that we didn't restrict ourselves with some parameters and so on. So it's our hope that the model is theoretical and can be easily modified if it's needed. So thank you for attention.
Thank you, Polina. And I would like to invite the last speaker, Fedorovsky Georgy, Russian Federation, St. Petersburg State University.
Hello, colleagues. My report is endochronic models of function thermoelasticity properties of wind glass reinforced plastics and their components. Dedicated to the 6th anniversary of victory over Nazi Germany and upstanding scientists and defenders of the Motherland, Kachanov Lazar Markovich. Introduction. The main problem of experimental of theoretical study, modeling and prediction on determined functional properties in the transverse direction of unidirectional on the bidirectional winding fiberglass plastic and their components are analyzed. The experimental date of the axial deformation of samples under temperature time effects of the region of significant structural transition are considered. The regularities of the relationship of properties, their dependency of the parameters of the structure and manufacturing techniques are investigated. NEF physical and mathematical model on the properties and their relationship, thermal expansion parameters, temperature time, correspondence and mechanical compliance of the materials are obtained with a optimal and convenience for describe and calculating on the determining function and for effective planning experiments. Experimental techniques, sample and apparatus. The method for obtaining the defining characteristics of materials were based on the development and manufacturing of raw samples and experimental setup for axial tension on conducting experimental of them and processing the data obtained. This an example of the manufacturing of winding fiberglass plastic. Sample of materials rods 3 bullet binder 1 and 2 in directional and bidirectional fiberglass 4 glass and fiberglass 12. General view of the test setup. Installation block diagram. The main experimental date. The determine function of the unidirectional, bidirectional, winding fiberglass, binder, and glass in trans 1 and 2 in transverse direction, 1, 2 in longitudinal. The main determining thermomechanical function of unidirectional in the transverse racing water director. Some models of determined properties and their relationships. Here are examples of relationships between the properties of the binder. We view asymmetric characteristic for vertical and horizontal in defining coordinates. Conclusion. The theory on vertical and horizontal scaling development by the authors on an effective method for mathematical, analytical, and numerical modeling on the determining functional properties and the relationship between materials, directory, and effective application telling experimental data with a role of 3.6%. When describing the defining properties, it allows you to take into account the influence of the structural parameters and manufacturing technologies by setting and the changed defining properties of the materials properties when its structure changes. For example, by the ratio introduction, and vertical scale depending on the parameter of the structure change уже vertical parameters. Technological parameters. To obtain various mutually complementary models of the interconnection of the materials properties, including an asymmetric and S-shaped type, is allows only describing different structural status of a material and the moderate of the strong temperature force and other influences. Improve accuracy and simplicity models by applying on the spline and logarithms method. It allows when to select the optimal measurement scheme and calculate the determined parameters and adhere and dramatic reduction in cost and time. Reference to this
These are works
work. Thank you.
Thank you very much, Georgi. And I would like to thank you very much, all speakers. If you want, we can ask questions, please.
I want to ask Polina Grigorieva.
Please.
Yes, I'm here.
I'm interested this theme, and I want to ask some questions. Can you explain the diffusion model, the accumulation of oxygen in the boundary layer near surface, and maybe you made some estimation about this, what height of this layer, or on what top you see some oxygen, or maybe something. I don't understand because everything very quickly. Okay, thanks.
So you mean where my boundary layer forms? Yes.
No, you said that it was diffusion model, okay? And this diffusion model you used for oxygen, okay?
For hydrogen.
Yes? Hydrogen, oh, yes. And this may have some estimations or what height of this layer or something else.
Well, from my model now, I don't have any specific or clearly seen layer. I just see the tendency that with the time, the distribution of the hydrogen stops, because normally if you will have a usual diffusion, it will go until every part of metal, I mean every metal throughout of itself will be full of hydrogen. But in my model, at some time, and very big time, the diffusion slows. Of course, it doesn't stop completely, just because I don't have any specific source or, of hydrogen when it can stop, but it really slows down at first. And the second is that the distribution of hydrogen, it quickly goes through the bulk of metal, and then it decreases to the center. I mean, so this is something that can assess that without any trapping, without any plasticity, which is actually we can see in experiments, we already have some tendency for forming boundary layer. And normally it's not high. Normally it's cylindrical samples. They are, well, you can put strains here, and then on boundaries there is hydrogen which diffuses through, and well, actually it forms. So this is a cylinder. Here we put some stresses, and here goes the hydrogen and forms this boundary layer of hydrogen in the metal.
Oh, thank you. It was very interesting. Okay.
Thank you. I see Viktor Yeremeyev up his hand, and please, Viktor.
Thank you for the possibility to ask. I have the question to the first speakers. It's independently who considered some viscosity in so-called reduced Cosserat continuum. What is the reason, physical reason for such viscosity? Why not to consider it like something like viscous micropolar model?
So, hello, it's a question for me, I suppose.
Okay.
And the aim was that we showed that with some viscosity, since we edit it, we allow waves to propagate in the former band gap where it used to be no waves at all before we at elastic case. So, and we changed.
Okay, the aim, I understood the aim, but what is why you assume such behavior, such dependence on viscous part?
So we probably I don't understand the question in the right way, but so we used some asymptotic approximations, and due to it we could see the behavior that we no longer had zero real part of wave number.
Okay, I understood. Thank you so much.
And please, Jean-Noël, next question.
Okay, thank you. I actually have a couple of questions for the same speakers, Sabina Isaeva and perhaps Alexandra Piatysheva. My question to Sabina is your follower moment or talk. Can you comment a little bit on this ingredient? Could it be something really part of the model, part of the material, or is it necessarily something external?
It is not a part of material. It's just a force, an external force that we go to our material. So we can get it from, I don't know, from magnetic fields, for example. Viscoelastic moment we can get from putting our material in some liquid. So it's not part of material. It's some external force.
Okay. And then I couldn't get if I couldn't see exactly whether the second model, the one in the second talk, had this, did it have the same ingredient? And for a question for Alexandra Piatysheva, well, it was a little bit too fast for me. I couldn't see if this was if this model had the same feature.
Sorry, I was interrupted, but so you're interested in where we used, so how we added this viscosity, or?
No, how, what is exactly, could you comment please on the difference between what you did, the model you used and the one used by your colleague, Sabina and Isaeva?
Well, but we, as far as I understood, we added different things to model because, well, Sabina changed, as far as I saw, moment, and I added viscosity, but yes, we had kind of the same behavior of material because, and the conclusions were the same.
But for instance, sometimes you use the rotational viscosity, and
yeah.
she used a viscous moment.
There is one moment. There is one very big difference in our conclusions. That, as I remember, Alexandra, she get that in for our one moment. For our matin part, she have dispersional curves that go in infinity, and my curves they have limit. So she just added the viscosity, and I added the viscosity torque. This is the main differences, and we don't. Yes, we have not same result, but very common.
Okay, I'll look more closely at the equations. Thank you.
Thank you. And please, Elena Grekova.
I just wanted to comment on the last questions. Sabina is right in the sense that in her model, we add the external torque. So it cannot be considered as a reaction of the medium because it is not materially objective. It's like a rotational Winkler foundation or maybe viscous foundation, but it's in the absolute space. In the case of Sasha, we have a similar thing for rotational viscosity, but it is not proportional to theta dot, to the velocity of microrotation. It is proportional to the velocity of microrotation minus rotor of velocity of translational velocity divided by 2. So the result is different also, as Sabina says, for high frequencies. Her system behaves almost as an elastic one as before, but in case of Sasha, this is not true. We have the behavior typical for classical viscous medium, viscoelastic medium. And Victor asked why we have chosen such a model. Well, it was just a model suggested by Ehringen, a classical Kelvin-Voigt model, but micropolar one, just because it was the simplest way to see how the viscosity changes the wave propagation. Initially, it was the motivation was to see how the dissipation changes things in the rotational seismology, because rotational seismology uses some Cosserat type theories, but usually they are very bad. Usually they even are not materially objective, like Makulog's ether or whatever. And the reduced Cosserat medium could be an appropriate model, is simple enough, but some dissipation is always present in reality. So we wanted to see how it will change the things. And it changes the things because instead of standing waves, actually we had in the forbidden zone, in the band gap, we had standing waves in the elastic case. And now we have decaying waves, but traveling ones. And what is interesting that the dissipation decreases in both problems. The attenuation decreases in the band gap due to dissipation. And thank you very much, Victor and Jean-Noël, for your questions.
Thank you, Lena and Victor. Please, I see your hand.
Okay, thank you, Lena, for explanation. Being a kind of gentleman, I should congratulate you with interesting results. Nevertheless, I have a question. What is difference, for example, if you consider it full, in certain sense, full viscosity, material viscosity, like dependence on all
you mean no elasticity, only,
yes,
only
rotational.
viscosity.
Yes, okay. Elastic part is reduced. Just a moment. Elastic part is reduced Cosserat continuum, whereas viscous part is just a micropolar fluid, for example, viscous micropolar fluid.
Ah, okay. You mean the full Cosserat for the viscous part that
Yes.
would be full Cosserat. Oh, well, I think it will be even worse. Well, actually, I mean, there will be more waves propagating because if now what we had, let's say we had some springs, some elastic connections broken, but we added dampers to each elastic spring which exists. If we in addition will add some viscous connections to the elastic springs which are broken, so I hope there will be more waves in this medium propagating, but we didn't do this. So this is just a hypothesis.
Okay, thank you so much.
I'm very glad that you like the work because Sabina is making, she will defend her bachelor work, and Sasha master one. So if you find it's good, then we are very happy, all the three.
Okay, I see. Good luck.
Thank you, dear colleagues. And I would like to ask a question, Evgeny Riabokon.
Yes, I'm here.
Please, Evgeny, what are the values of the mechanical properties of on static and dynamics experiments? You compare, but I would like to see values.
Yes, sure.
Mechanical modulus.
For example, in which regime are you interested in, or in static or dynamic?
What?
So here on the, for example, let me go back, maybe start from the beginning. So yeah, here you can see uniaxial compressive strength in static and Brazilian tensile strength in static. So you can see, so that's 37, 38, 38, depending on diameter. And if we go further till the dynamic experiments, you might see that they are reduced.
Okay.
So the reduction is about 20% in comparison with static results.
Thank you.
Yeah, here.
Svetlana Trashenko, please.
Question to me?
I have question to Evgeny Riabokon. What is the value of strain velocity during dynamic experiments?
Strain velocity.
Yeah. Or speed?
Yeah, I actually cannot tell it right now. What was the speed? So the frequency was different. It was varying from 15 to 40 hertz. That was the frequency. And the amplitude, vertical amplitude was varying from 1.45. You can see it here.
And could you calculate the velocity? No.
Probably not.
No. Thank you.
And now I cannot see the questions. Our discussion is over, and our session is over. And I would like to say once more thank you for all participants, and goodbye.